Sometimes, solving for x in terms of y is mathematically exhausting or impossible. The shell method allows us to keep our functions in terms of x while rotating around vertical lines, making the integration process much more straightforward and less prone to errors. Before we proceed, remember that the foundation of the shell method is the Riemann sum of thin vertical rectangles. We take the height of the function at a point x and multiply it by a tiny change in x, which we call dx. This rectangle will become our shell. Imagine unfolding a thin cylindrical shell into a flat rectangular prism. The length is the circumference, 2r, the height is h, and the thickness is dr. Multiplying these three dimensions gives us the volume of a single shell. Summing these shells gives us the total volume. When rotating around the y-axis, the radius is simply the distance from the origin to x. The height is the function value f, x. Thus, the standard formula is the integral from a to b of 2 pi times x f, x is dx. But what happens when the axis moves? This is the core concept. If we rotate around a line x equals h, the radius is no longer just x. It is the horizontal distance between our slice at x and our axis of rotation at h. We calculate this distance by subtracting the smaller value from the larger value. If the axis of rotation is to the left of the region, say at x equals -2, the radius is x minus -2, which simplifies to x plus 2. The radius increases as we move further right into the region. Conversely, if the axis is to the right of the region, for example at x equals 5, the distance from our rectangle at x to the axis is 5 minus x. Always ensure your radius expression is positive for the interval of integration. The height of the shell is determined by the boundaries of your region. If the region is bounded by two functions, the height is the upper function minus the lower function. The thickness remains dx because we are summing vertical shells along the x-axis. Let's work through an example. We have the region under y equals x squared from x equals 0 to x equals 2. We are rotating this around the vertical line x equals -1. First, let's identify our radius and height. The radius is the distance from the axis at -1 to a generic x, so r equals x plus 1. The height is determined by the function, so h equals x squared. Our limits of integration are the x-bounds of the region, 0 to 2. We set up the integral, 2 pi times the integral from 0 to 2 of the radius, x plus 1, times the height, x squared. Multiplying these out gives us the polynomial x cubed plus x squared, which is easy to integrate. Evaluating the antiderivative at the bounds, we get for plus 8/3 minus 0. This simplifies to 20/3. Multiplying by 2 pi, we find the total volume is 40 pi over 3 cubic units. Visualizing the shells helps confirm this result. Now, let's look at a case where the axis is to the right. We rotate the region under y equals square root of x from 0 to 4 around the line x equals 6. Notice the gap between the region and the axis. Since the axis is at x equals 6 and our x values are between 0 and 4, the radius is 6 minus x. The height is simply the square root of x. The setup is now ready for integration. Distributing the square root of x, we get 6x to the 1/2 power minus x to the 3/2 power. By using the power rule for integration, we can solve this term by term to find the volume of the resulting solid. In more complex cases, the height is the difference between two functions. Here, the line is above the parabola. The radius is 3 minus x because the axis is at x equals 3. The process remains identical, 2 pi times radius times height. A common edge case occurs when the region is below the x-axis. Remember that volume must be positive. The height of your shell is the top boundary minus the bottom boundary. If the top is the x-axis, the height is 0 minus the function value. How do you choose between methods? The shell method uses slices parallel to the axis of rotation. If your rotation axis is vertical and you want to integrate with respect to x, use shells. If you prefer integrating with respect to y, use washers. The most common mistake is reversing the radius subtraction. If your radius is negative, your final volume will be negative. Always check, is my right value minus my left value positive for every x in my interval? Another error is forgetting to convert all terms to the variable of integration. In the shell method for a vertical axis, everything inside the integral, radius, height, and limits must be in terms of x. Don't forget the constant 2 pi. Because we are dealing with the circumference of the shells, this constant is essential. A common mistake is to perform the entire integration correctly but leave out the 2 pi in the final answer. To summarize, first, determine your limits of integration along the x-axis. Second, define the radius as the distance from x to your shifted axis. Third, define the height using your functions. Finally, assemble the integral and solve. The shell method is a powerful tool for finding volumes. By thinking of the solid as a collection of nested cylinders, we can solve complex rotation problems by simply identifying the radius and height relative to the axis of rotation. Here is a quick question: if your region is between x equals 1 and x equals 4, and you rotate around the line x equals 5, what is the radius expression? The answer is 5 minus x, because 5 is to the right of the region. Thank you for watching. Generated by Vision Solve AI.